Hi guys, we're going to finish up some stuff on inverse functions. I will let you know I've had some technical difficulties while trying to record this video. This is like probably the 5th time I've tried, so I'm going to do the best I can. I may have to stop the video and start over, so you may have multiples to go, but we'll see what happens. Alright, so we're going to finish up just with 3 quick topics on inverse functions. The first topic, what does the graph of a one-to-one function look like? The answer to that is that it passes the horizontal line test. If something passes a horizontal line test, it means that if we take a horizontal line and pass it over the graph of the function, it won't touch that function in more than one place at a time. And so in this case, we can see that this graph on the left, this linear function, does pass the horizontal line test, and therefore it is what we would consider a one-to-one function. Now, why is it important for us to understand what one-to-one functions look like? Well, I'll remind you that one-to-one functions are the ones that have inverses. If a function is not one-to-one, it does not have an inverse. Okay. Also, I want to remind you, as I've got things already written down, that if you need to pause the video so that you can get caught up, please do that before you watch what's happening. All right. On this graph, we can see this quadratic graph. If I apply the horizontal line test to it, as soon as I pretty much hit the graph, I've now got a horizontal line which touches the graph in more than one spot at a time. And so that is an example of something that is not one-to-one. Okay, so that one is not one-to-one. And in fact, you'll notice on your homework that you did not have any functions where you were finding the inverse of a quadratic. And we're going to talk about finding the inverse of a quadratic here in just a minute. Okay? All right, the next topic we want to talk about is what do the graphs of inverse functions look like? So what does the graph of inverse functions look like? Okay, and the answer to that is a reflection over the line y equals x. Okay, and we might need to discuss what that line y equals x looks like. So again, if we're graphing a line and we want to choose values for x and find out what y is, if I chose the value 1 for x, then y would also be 1, so we would have the point 1, 1. If I chose 2 for x, then y would also be 2. If I chose negative 1 for x, y would also be negative 1, and 0, 0. And so we have this set of ordered pairs, which creates this line y equals x. Now, when we talk about reflecting something over the line y equals x, it kind of makes sense when we're dealing with inverse functions. If you think back about how we find inverse functions, we are, well, let's see what I want to do here. This one, and this one. One of the steps that we had when we were finding an inverse function is to switch the roles of x and y. And so if I'm looking at a piece of a function, so you'll notice that I have endpoints, I don't have arrows on the end of that, and I say, okay, well, the points on this function are negative 2, 1, 0, 2, and 1, 4. Okay, we can actually find the inverse by switching the roles of x and y. So if I switch the roles of x and y here, I'm actually going to get the ordered pair 1, negative 2. And I would graph that and it would be right here. Okay. When I switch the roles of x and y for the point 0, 2, I get 2, 0, which would be here. And when I switch the roles of x and y on this third point, I get 4, 1. So over 4, up 1. And you can see that if I graph those, that those look pretty much like we took this piece of this function and we reflected it over the line y equals x. So you're going to have a few problems today where you are getting a picture of a graph that looks similar to this potentially, and you're reflecting it over that line y equals x by taking some ordered pairs and switching the x and the y values. Okay? All right, so in addition to that, and also looking at some graphs of functions and determining if they are one-to-one, you're going to look at a couple of problems where you are finding the inverse of a particular quadratic function. Now, very quickly, as we talk about quadratics, we said that they are not one-to-one. Okay, so if I look at a quadratic that looks like this, and it has a vertex maybe right here, I say, oh, okay, that's great. It's not one-to-one. However, if I restrict this and say, well, but I only want to look at one piece of it, let's say, for instance, I only want to look at the left side of that graph, okay, from here and up, right? I only want to look at this portion of the graph. Is this portion of the graph one-to-one? And we could use the horizontal line test and find out that it is, in fact, one-to-one. And so we could find the inverse of just this portion of the graph. And so that's what you're going to find when it asks you to find the inverse function of a quadratic, is that there's going to be some sort of restriction on its domain. So let's look at an example of that. Y equals, or sorry, let's start with f of x, is x minus 1 squared plus 2. And we're going to say x is less than or equal to 1. Okay. Now, just as a point of reference, this is a quadratic. If we could graph that on the computer or something, that has a vertex that is at 1, 2, so it's right here. Okay, so it would look something like this, maybe. Okay. But this little piece right here, this x is less than or equal to 1, says, oh wait, I only want to look at the places where x is less than 1, meaning I'm not paying attention to anything over here on the right-hand side, and in fact I can just get rid of that, because the only thing I want to graph for this function starts here, and we come up this direction. Okay. So we're finding the inverse then of just this section. All right. Now, the steps for finding the inverse are going to be the same. We're going to substitute y for f of x, switch the x and the y. Then we're going to solve this for y. So I'm going to subtract 2. And then at this point I'm going to take the square root of both sides. When I take the square root of both sides, keep in mind that when we do that, we get positive or negative. Okay? And we need to talk about that for a quick moment, because this is the problem with finding the inverse of a quadratic, is when we take the square root of both sides that we actually get 2 answers. Well, I don't want both answers. I only want to deal with one of them. So here's how you're going to determine which one we want to deal with. You're going to look at this initial domain restriction. This one says x is less than or equal to 1. Since this is a less than and we're looking at the left side, we're actually going to be focused only on the negative square root. Okay? If this had been a greater than and we were looking at the right side of this graph, then we would want to use the positive square root. Okay? But again, because it's a less than, it's going to be a negative square root. We're going to add 1 to both sides to get 1 minus the square root of x minus 2 is equal to y. Or the inverse of f of x is 1 minus the square root of x minus 2. And there's our inverse function. Okay. So again, a lot of the steps are the same, except for we have to be cautious about which we choose here, which radical or which square root we take, is the positive or the negative, based on the original inequality for our domain. Okay. There's some really good examples in the book if you want to take a look at those also. But your assignment for today is going to be on page 271 through 273. You're going to do 9 through 16. They're going to be looking at some graphs and determining if they are one-to-one. You're going to do 31 through 34, where you're going to be looking at graphs and figuring out what the reflection over that line y equals x looks like. And then also 63 and 64, those are both finding the inverse of quadratic equations with those domain restrictions. Okay, good luck, and I will see you guys next week. Bye-bye.